Alrighty, worksheet number 3 is what we're going to be talking about today. This is a big worksheet with a lot of difficult problems on it. So we'll go through a lot of this and see where it takes us today. So page 1 overall wasn't too bad. Number 1, we've got that 5 kilogram mass there, and it's hanging by that string. So your equation for your force would just be tension force up minus gravity down, and that's what your force diagram should look like. Tension up, gravity down. So your equation is tension minus gravity equals 0, therefore tension is equal to gravity, and because we know the mass, we can find what force of gravity is. 5 times 9.8, and so that's 49. So 49 newtons is all you should have for number 1, case A. Case B is pretty much the same thing, but now you've got 2 strings. So your force diagram would have 2 tension forces up and gravity going down. So equation would be tension 1 plus tension 2, because they're both going up, minus gravity down equals 0. And when you do the math there, no surprise, you're going to get half the answer for each string as you got in case A, because that 49 newtons is divided up between those 2 strings. Number 2, the 4 kilogram mass, you do the same way that you did number 1. Tension up minus gravity down equals 0. Therefore, tension on the 4 kilogram mass is equal to force of gravity. And force of gravity is just mass times 9.8. 4 times 9.8 is equal to 39.2. And that is the answer to the 4 kilogram mass tension force that's acting just above it. The tension that's acting on the 7 kilogram mass is a little bit different. So for the 7 kilogram mass, we've got our 7 kilogram mass here. And in terms of forces, it's got gravity down. It's got tension up. But that's not all, because it's also got the tension, and I'll say T4, tension from the 4 kilogram mass, pulling it down as well. I'll call this tension 7. Might as well. So if I wanted to then create a force equation for this, I've got tension going up, holding the 7 kilogram mass there, minus the 2 tensions going down, the 2 forces going down, I should say. Force of gravity and the tension from the 4 kilogram mass. And that's all equal to 0. So in order to solve for the tension force, we got to put both of those 2 things on the other side. Gravity plus tension 4. And we already know what tension 4 is. We calculated that, the last thing I mentioned. So tension 4 was 39.2. And force of gravity is just mass times 9.8. And so our mass here is 7. So 7 times 9.8 gives us our gravity, and that is 68.6 newtons. So when you go ahead and add these 2 things together, you're going to get roughly 108 newtons. And that there would be your tension for the 7 kilogram mass. Another way to think of this is just that string is holding both the 7 kilogram mass and the 4 kilogram mass. So you could just think of it as one 11 kilogram mass and solve it the same way that you solved number 1, case A, and the tension for the 4 kilogram mass. But there you go anyway. Okay. Next up, we've got number 3. And this is an interesting little problem here. So there's that box hanging. We've got two strings coming off of it, and they make 30-degree angles, each of them. And our goal is to figure out the tension in each cable. So we want to start with a force diagram here. Gravity is going down. And of course we've got our two tension forces. Now it tells us that the object weighs 25 newtons. So that is a force. If it told us it was 25 kilograms, then for force of gravity we'd have to go 25 times 9.8. But it doesn't tell us that. It tells us directly the newtons. So that means that's what your force of gravity is already equal to. So 25 newtons going down. So if I want to solve for these tension forces, you can tell they're both going to be the same value, whatever it is. If I want to solve for those, I got to look at what's happening, vertically or horizontally. And the only piece of information that we have is a vertical piece of information. So the best thing we can do is take a look at what's going on vertically here. So we'll use the one on the right here. So that tension force is going partially upwards, Ft2y. It's also going partially across in the x direction. So vertically, I've got Ft2y here and Ft1y over here. Those are both going upwards. So my force equation is going to be Ft1y plus Ft2y minus gravity equals 0. Everything going up minus everything going down. That's all there is to it. So if that's the case, I can move force of gravity to the other side. And I know force of gravity is 25 newtons. And so if both of these are the same value, and together they're going to add up to 25, you just got to divide 25 by 2 in order to get both of them. So 25 divided by 2 is equal to 12.5. So that's what your tension 1y and tension 2y are equal to. So there you go. So what that means then is I know this side of the triangle is 12.5. And if I'm looking for my tension force, I've got enough information to do that now. I have the opposite side of the angle, and I have the hypotenuse there. So if I want to figure out the hypotenuse, I'm going to use a sine function because I've got the opposite side, and I'm looking for the hypotenuse. So sine of 30 is equal to opposite, which is 12.5, over hypotenuse, which is tension 2. And so to solve for tension 2, you multiply both sides by tension 2, and then you have to divide both sides by sine 30. So 12.5 over sine 30, and as long as your calculator is in degree mode, you're going to end up with an answer of 25. So 25 newtons is equal to Ft2. It's also equal to Ft1. 25 newtons is your answer there. For the next part of this, it says do the same thing but with a 5-degree angle. So if we were to change this angle to 5 degrees and do all of this again, we would end up with a tension force of 143 newtons, which is much, much larger. And that's page 1. Page 2. A couple big ones on this side. So, we've got this mass and it's hanging from these two strings, the sort of thing that we've seen before. If I want to figure out the value of tension force 2 and make the equation for the forces acting in the x direction, first thing I got to do, no surprise, is create a force diagram. So, gravity is going down. I've got tension 1 going to the left. And I've got tension 2 going up at this funky little angle here. And that angle is given as 30 degrees. Now I'm used to having information about this angle. So personally for me, I'm going to just put 60 degrees here because they have to add up to 90. And I'm used to dealing with that angle. If you're cool both ways, do whatever you want, but that's where I like to live. So you can kind of see where this is going to go. This is the only force that's not acting vertically or horizontally, so we have to divide it up into its x and y components. So ft2y is there. This here would be ft1y, ft2x, and those are your components. So when you're writing the equation for the forces acting in the x direction, you've got two of them. Tension 2 in the x direction and tension 1. So your force equation is going to be ft2x minus ft1 equals 0. Why did I pick ft2x to be the first one here? It's going to the right. Usually, because these forces, it doesn't really matter which one you make positive or negative. But for me, if it doesn't matter, I just say whichever one's going to the right is going to be the positive one. You can do whatever you want. So, what's the next question? What is the value of ft2? So if I'm looking for tension 2, which is the hypotenuse here, then what I need is more information about this triangle. And I've got a good amount of information. I know ft1 is equal to 30. 30 newtons is equal to tension 1. So, from the equation that we just wrote, you can see that tension 2 in the x direction is going to be equal to tension 1, which is 30 newtons. So then, if I want to use that information to solve for ft2, it should be pretty straightforward. And then, this is 30. 30 newtons is that side of your triangle. So, if I want to solve for the hypotenuse, and I have my adjacent side, I'm going to be using cosine, because cosine takes into account the adjacent side and the hypotenuse. So cosine of 60 is equal to adjacent, which is 30, over the hypotenuse, which is what we're looking for. So to get ft2, I multiply both sides by it, divide both sides by cosine 60, and when you do the math, you should end up with 60 newtons. That's ft2. Letter B then says write the equation for the forces acting in the y direction. And what is the force of gravity? So for this one, we got to do a little bit more with our force equations. And again, that's how you want to approach each and every one of these problems. So if I want to look at my force of gravity and figure that out, I'm going to have to look at the vertical forces. And so what's going on vertically? Well, I've got ft2y going up. I've got gravity going down, so I subtract them. ft2y minus gravity equals 0. Therefore, ft2y is equal to force of gravity. So all I got to do is find ft2y in order to get my gravity. And you can do that pretty easily. It's the opposite side of our 60-degree angle. So I'm going to go ahead and use sine here. I know that the hypotenuse is 60. Figured that out in the last part. So sine is equal to opposite over hypotenuse. So sine of 60 is equal to ft2y over the hypotenuse, which is 60. So tension in the y direction is equal to 60 times the sine of 60. Kind of an interesting equation there. And when you do that math, you'll get 52 solid newtons. So there you go for number 4, letter B. Next up, we've got number 5. And this is our friend the incline. We all just love inclines to death. Emphasis on to death. So, incline time. And this one's going to look a lot like the one that we had in our notes here. We've got our block. The block is 20 kilograms, and it's being held in place by a little string. And if I want to solve for stuff in this, what I got to do, I got to start with my force diagram. So if I want to draw my force diagram, I'm going to start with gravity. So gravity's going down. Normal force is going to go up at that angle because normal force always goes perpendicular to your surface. And you got your string going that way, so that's tension force. And that's kind of what our raw force diagram is going to look like. Of course, it doesn't stay there. It gets a little bit more complicated. Whoa, that force of gravity is a little bit angled there. That might bother me. That's better. So, ultimately we're looking for tension force here. And in order to go anywhere with this, we have to remember how we approach these problems. And what we have to do when we've got two forces that are not in line with the x and y axis is we take our x and y axis and we just rotate it slightly. And in this case, we'll be rotating it a little bit clockwise. So my y-axis is going to match up with the normal force. It's my new y-axis. My x-axis is going to match up with the tension force. And from there, I'm going to create my force of gravity in the x and y directions. And the way you do that is you draw a little dotted line that gets to those new axes. And if it hits it at a 90-degree angle, you can use that to draw your force of gravity in the x and y direction the appropriate length. Again, like I've said before, I don't care if your arrows are the right length. All I really care about is that you know that this is the hypotenuse of both of these triangles here. That's the important part. We also have to go ahead and put our angles in. And this 30-degree angle is on the wedge here on this corner. And you can see if I just lifted this up and slid it in, it would slide right in here. It would not slide in here. I'd have to flip it around. So because the wedge is on this side, it matches up with this angle. So that's 30 degrees. This would be 60 and 30. and you get the idea. And now we're finally done with our force diagram. And now we got to hit up our force equations. And the first part of number 5, we're looking for tension force. So that means we better start looking at what's going on in the x direction. I should also label my force of gravity in those directions. This is force of gravity in the x direction, and this is force of gravity in the y direction. So horizontally, along the surface here, our equation is going to be tension minus force of gravity in the x direction is equal to 0. So, if I want to figure out my tension force, all I got to do is solve for force of gravity in the x direction. And I can do that because this problem gives me the mass. And remember that force of gravity is just mass times 9.8. So 20 times 9.8 is equal to 196. So that means the hypotenuse of this triangle is 196 newtons. So if that's the case, now I have enough information to figure out force of gravity in the x direction. So that's the adjacent side of this 60-degree angle. And so that means cosine of 60 is equal to the adjacent side, which is FGX, over the hypotenuse, which is 196. And if you do that, you've got an expression for FGX. It's going to be equal to 196 times the cosine of 60. You're multiplying both sides by 196 to get that. And when you do that math, you're going to get 98 newtons. 98 newtons is equal to force of gravity in the x direction, which is also equal to your tension force. Whew. All right, so that's the first one. Now the second part of this asks for the value of the normal force exerted by the ramp. So now we're going to look at things in the y direction, because that's the direction that contains the normal force. So in the y direction, we've got normal force up, and we've got gravity in the y direction going down. So our force equation is normal force minus gravity in the y direction is equal to 0. So therefore, normal force is equal to force of gravity in the y direction. So if we can find FGY, we are home free for number 5. So FGY is over here. It is the adjacent side of this 30-degree angle. So I'm going to use cosine again. Cosine of 30 is equal to adjacent, which is FGY, over hypotenuse, which is 196. Therefore, you've got an equation for FGY. Force of gravity in the y direction is equal to 196 times the cosine of 30. And when you go ahead and you do that, you are going to get an answer of 170 newtons. So 170 newtons is equal to your force of gravity in the y direction. And because your force of gravity in the y direction is equal to normal force, you've got your answer for the normal force. And that's number 5. Number 6. I'm just going to briefly talk about number 6 here. I don't want this video to get way long on us. Number 6, it's going to be the same type of force diagram. I'll just go ahead and draw it kind of quickly here. So, gravity is down. Normal force now is going to be up and to the left, because that always goes perpendicular to your surface. Tension force is always parallel to the surface. And so that's going up and to the right. So, I mean, you can see where we got to go from here. We've got to rotate our x and y axes again, and we can do that. Y-axis, again, always goes perpendicular to the surface, same as the normal force. X-axis goes parallel to the surface with the tension force. So you can get your force of gravity arrows in the x and the y direction. There's your FGY. Here's your FGX. And then you can put those little angles in. 35 degrees would fit in on the right side. So as we alternate, they have to add up to 90. So it'll be 35, 55, 35. You get the idea. So this one's asking for the mass of the object on the ramp, and that's sort of interesting there. If you're going to look for that mass, the hint is that we know tension force. Nothing is moving, therefore your tension force is just equal to that hanging 20 kilogram mass times 9.8. The same problem we did at the very beginning of this worksheet here. So what you need in order to figure out your mass is you ultimately need to solve for force of gravity information here. And because we've got tension force, that's a pretty strong hint that we ought to look horizontally along our ramp here. And so your equation in the x direction is tension force minus gravity in the x direction is going to be equal to 0. And so we know tension force. Tension force is 9.8 times 20. So that's 196. And therefore, 196 is equal to force of gravity in the x direction. So this here is 196. And you can see now we've got enough information to find the force of gravity. Force of gravity is the hypotenuse here. And so we would use a cosine function. Cosine 55 is equal to adjacent, 196, divided by the hypotenuse, which is force of gravity. And you can then use that to get your force of gravity. And once you have your force of gravity, you can get your mass. Because say your force of gravity ends up being equal to, it would be higher than 196. So that, let's say force of gravity just ends up being equal to 300. If your force of gravity is 300, remember that force of gravity equals mass times g. So it would be 300 equals mass times 9.8. And divide both sides by 9.8, and your mass pops right out of there. Again, 300 isn't your force of gravity. I'm just using that as an easy number for an example. You should end up getting a mass of 34.9 kilograms for this one. So that's the end of that story. Last page, 2 problems. This shouldn't be too bad. And they're both roughly the same. One's pulling, one's pushing. But of course, to make our lives extra interesting, they're all happening at an angle. So, let's dive in here. Number 7, the guy is pulling, and he's pulling up and to the right. So our force diagram is going to look sort of like this. Gravity is going down. Tension force is up at a 30-degree angle. And it's moving across the floor at a constant speed. So what that means is there must be friction here opposing that pull. Because if there was no friction and he was pulling, it would be picking up speed. But because it's moving at a constant speed, there's got to be some friction there. So this is tension force. Now, in order to finish this force diagram, you got to remember this tension force is acting not just in the x direction, not just in the y direction, but both directions. So I might call this tension in the x direction going up. It's got tension in the y direction. And that's as far as I can go with a force diagram from here. Letter A says write the equation for the forces acting in the x direction, and then find the force of friction. So, in the x direction, we've got two forces. We've got tension force and we've got friction, and friction is always negative. So that means my force equation is going to be Ftx minus force of friction equals 0. If I want to solve for my force of friction, I'm going to chuck it to the other side of the equation and find out very quickly that force of friction is equal to the tension in the x direction. So, all I got to do is find my tension in the x direction. Hopefully I'm giving some information here. Alright, I've got a 50 kilogram box, and he's applying a 200 Newton force. So 200 newtons is my hypotenuse. And yes, I do have enough information then to figure out tension in the x direction. So I have my hypotenuse, I'm looking for the adjacent side, and that means I'm going to use cosine, because cosine is equal to adjacent over hypotenuse. So adjacent is Ftx, hypotenuse is 200, so if I'm looking for Ftx, multiply both sides by 200. And if you plug that into your calculator, which is in degree mode, you're going to end up with 173 beautiful newtons. And if 173 newtons is equal to tension in the x direction, it's also going to be equal to your force of friction. So, that's letter A. Letter B, now we got to do an equation for the y direction. And we got to solve for normal force. Oh, and I actually, I didn't put the normal force into the force diagram. So we're going to do that too. So, vertically, you're going to have a normal force here. Don't forget about that. And that normal force, because you're pulling up, is going to be smaller than your force of gravity, because as you're pulling up, the table doesn't have to exert as much effort or force as you're pulling it up. So normal force is up. It does exist. So if I'm looking vertically, then my force equation is going to be whatever's going up minus whatever's going down. So going up, we've got two things. We've got normal force, and we've got tension in the y direction. So, because they're both going up, they're going to be added together. And that's all minus gravity equals 0. That is your force equation for the y direction. Now it says, find the normal force. So if I'm going to find the normal force, I am just going to isolate it in this equation. So that's equal to force of gravity minus tension in the y direction. And so I just got to find these two things, and that'll be it. So force of gravity is pretty simple. Force of gravity is just mass times 9.8. And it says our mass is 50 kilograms. So 50 times 9.8 is equal to 490. That part's easy enough. Tension in the y direction is the opposite side of our triangle. And we know about the hypotenuse, so I'm going to use a sine function here. So sine of 30 is equal to opposite, which is 200, over the hypotenuse. Whoops. I'm making all sorts of mistakes here. That makes it more fun. So again, this is your hypotenuse. Opposite side is FTY. So opposite side goes on top. Hypotenuse goes on the bottom. Therefore, FTY is equal to 200 times the sine of 30. And when you go ahead and do that, you get an even 100 newtons. So 490 plus 100 is equal to 590, I think. And so that then will be equal to your normal force, 590 newtons. Nope. We're subtracting the two. So 490 minus 100 is 390. So 390 would be your answer then. And that is number 7. Finally, we're going to get to problem number 8. So let's take a look at that one. And this is the end. This is the last one. Thank goodness, right? So this is kind of like the same example, except now we're pushing down instead of pulling up. So this guy's pushing down at a 50-degree angle. Force of gravity is going down. He's pushing down at that 50-degree angle there. So there's 50 degrees. And again, we're moving with a constant speed. And so what that means is that there's friction here. Because if there was no friction, it would be picking up speed as he's pushing. In addition to that, we've got normal force. Normal force is going to go up, and it is going to be larger than gravity in this case. And it's going to be larger because as he's pushing down, the table, or the floor in this case, has to exert more effort in order to keep the object from falling through, because he's pushing down, he's giving it extra pressure. So normal force is bigger in this case. And because he's pushing, we call that force an applied force. And just like always, our applied force is acting both in the x and y direction. So I would call this the applied force in the x direction, and I'd call this the applied force in the y direction. And that's all she wrote for the force diagram. Now it says write the equation for the forces acting in the y direction and then find the normal force. So let's find the normal force here. Vertically, we've got 3 things going on. Normal force up, gravity down, and applied force in the y direction down. So what that means is that normal force is going to be listed first. It's going up. But it's being opposed by these 2 things. So applied force in the y direction is going down, and so is gravity. And so that's why we're subtracting both of these from the normal force. And that whole thing is going to be set equal to 0 then. So if I want to figure out my normal force, I isolate it in the equation. And you can see these 2 things are just going to be added together then. When we yank them out from this side of the equation and we toss them over to the other side, the negative becomes positive. So that goes away. So if I want to figure out my normal force then, I need to figure out both of these things. Well, force of gravity is pretty straightforward. Mass times 9.8. So looks like he's pushing a 2-kilogram broom. So 2 times 9.8 is going to be 19.6. That is our force of gravity. Applied force in the y direction, this is a different story. This is the opposite side of our 50-degree angle. And it tells us that he's using a 5-Newton force to push that broom. So our hypotenuse here is 5 newtons. So if we go ahead with this then, and solve for the opposite side of our angle, we're going to be using a sine function. So sine of 50 is equal to opposite, which is FAY, over hypotenuse, which is 5. And in order to solve for FAY, multiply both sides by 5. And when you do that math, you're going to end up with 3.83 newtons. So in order to get your normal force then, you add your applied force in the y direction to your force of gravity, and out pops your final answer. Normal force is equal then to 23.4 newtons. And we're almost there. One more to go. Letter B is the last equation that we got to do here. So find the forces acting in the x direction, and then calculate the force of friction is what we're going to be doing. In the x direction, we've got two things going on. We've got applied force and we've got friction. So our force equation is simply going to be applied force in the x direction minus friction equals 0. So if I want to figure out the force of friction like it's asking, I chuck it over to the other side of the equation. Applied force in the x direction is equal to friction. So I just got to solve for the applied force in the x direction if I want to get my friction. And I can do that. It's the adjacent side of this 50-degree angle, so that means I'm going to be using cosine. So cosine 50 is equal to adjacent, which is FAX, over the hypotenuse, which is 5. That's given to us. And if I want to solve for the applied force in the x direction, it's just a matter of multiplying both sides by 5. So when you do that math, you should end up with an answer of 3.21 newtons. And that is your applied force in the x direction. Letter C then just says if the force of friction were suddenly reduced to nothing, what would happen to the broom? If there was no friction here, then you have a force to the right with nothing opposing it. And if that's the only force you have, that broom is going to pick up speed. It's going to accelerate. So, there you go. Worksheet number 3. Again, with all this stuff, the more you practice it, the better you're going to get. And that's the end of worksheet 3. Have a good one.